Okay. Hello, everyone. I am thrilled to introduce Ben Adcock as our speaker this week. Ben is an associate professor at the Simon Fraser University in Vancouver, Canada, where he is currently serving as the Pacific Institute for the Mathematical Sciences SFU site director. He's won many awards despite his sprightly young age already, including the Canadian Applied and Industrial Math Society PIMS Early Career Award, an Alfred P. Sloan Research Fellowship, and the Leslie Fox Prize in Numerical Analysis. And today he's going to talk to us about the troublesome kernel. So I'll turn things over to you, Ben.
Great, thank you, Mark. So first of all, I'd like to thank the organizers, in particular Mark, for the invitation. It's very nice to be able to speak. Also, I'd just like to thank the organizers generally for putting this, this excellent seminar series on during this time when we're all sort of missing having conferences to go to. It's very nice to be able to connect remotely and hear interesting talks. So, So as the title says, this is a talk about inverse problems and in particular inverse problems in imaging. And what we've seen in the last couple of years is that there's been a lot of activity on using deep learning to perform image reconstruction. So this means training a neural network to, given some measurements, say coming from an MRI machine or something like that, reconstruct the image. And what I don't want to do in this talk is to propose another deep learning strategy to do this. What I want to do is highlight a phenomenon that I don't think has been explored sufficiently, which is that deep learning approaches for image reconstruction problems have a tendency to be unstable. By this, I mean that you can make small perturbations to your measurements and create large artifacts in the outputted images. So this talk is sort of divided into sort of 3 bits. So I'll start with a sort of introduction to image reconstruction and deep learning for image reconstruction. And then I'm going to sort of experimentally highlight, show this phenomenon. So I'm going to construct examples and show the different artifacts that can arise due to this instability. Then in the next part of the talk, I want to dig into the sort of mathematical underpinnings of why these instabilities arise and try and identify the mechanisms that cause deep learning approaches to become unstable in this way. So then in the final part of the talk, with that in mind, obviously, you know, our goal is to construct stable algorithms for image reconstruction. So I want to spend the last part of the talk talking about what we might do in the future. So I'll give the game away here and say that I'm not going to propose a radical new strategy that's going to make everything stable, but hopefully I'm going to give some guidance informed by the sort of mathematics that comes up in the earlier part of the talk to what we can do in the future to try and get sort of more stable approaches. Okay, so let me jump into the first part of the talk. This talk is about image reconstruction. So we know that reconstructing an image from measurements is a fundamental task that in many different applications. So medical imaging, such as MRI or X-ray CT, or scientific imaging, such as various types of microscopy or tomography, and also industrial imaging like seismic imaging, etc., etc. So in this talk, we're going to assume a very simple mathematical model for the image reconstruction problem. So we're going to consider an image X as a vector in Cn, and its measurements are going to be of the form y equals ax plus e, where X is the discrete image, A is what we'll call the measurement matrix, so this models the acquisition process, and E is the measurement noise. So this is a very simple model. You can think of sort of much more sophisticated models. So maybe rather than a discrete model, you have a continuous model. Maybe the acquisition process is not linear, maybe it's nonlinear. This can occur in applications, but for the purposes of this talk, we're just going to look at this simple model here. just a couple of examples to sort of set sort of concepts in our minds. So if we think about Fourier imaging modalities, so for example, MRI, then here the measurement matrix A is going to be a subsampled Fourier transform. Yeah, so it's going to take this form. If we think about radon imaging, so various types of tomography, including X-ray CT, then A is a subsampled discrete radon transform. And if we're looking at sort of optical imaging, so things like microscopy or lensless imaging or something like that, then you might have A being a subsampled Walsh-Hadamard transform, for instance. Okay, so the main thing that makes this challenging problem, as I think many people are very familiar with, is that often in practice we're limited by the number of measurements we can take. So M is the number of measurements throughout the talk, and often in applications, M is much smaller than the ambient dimension N. So this manifests itself in different ways. So it might be related to the acquisition time. This is the case in MRI, for instance, where loosely speaking, the number of measurements you can take is proportional to the amount of time you sit in the scanner. And for various reasons, one of the key challenges in MRI is to try and reduce the acquisition time. In something like X-ray CT, the number of measurements is again loosely related to the radiation dose, and of course there are limits on how much radiation you can expose a patient to per year, which limits the number of times a patient can be scanned. In other applications, say for instance seismic imaging, this might come up as the cost. So seismic imaging, you've got to purchase and maintain sensors over the surface of the Earth, so each sensor is going to cost you money. And then in other applications, this might come up as power, for instance. So if you want to build any kind of portable imaging system, then it can't afford to draw a lot of power. So, so compressive imaging is sort of the term that we use to describe the field where we look to design algorithms for image reconstruction that try and deliver as high accuracy images as possible from using as few measurements as possible. And the point is that this is really computational imaging, where we focus on building better algorithms to do image reconstruction rather than completely redesigning hardware or something like that. Okay, so I want to say a couple of historical remarks about compressive imaging or about image reconstruction, and let me start with sort of the pre-2000s world, and I'm going to make some simplifications here. So this is oversimplification of the history, but I'm going to do it anyway. So pre-2000s, more or less the standard approach was based on something fairly simple. So you take your measurements y, you zero pad them to get a vector y tilde in Cn, and then you apply some kind of left inverse of your forwards operator. So if you're doing Fourier imaging, then this is an inverse zero padded FFT. Radon imaging, then it's typically a zero padded filtered back projection. So of course, this hides the many variations and intricacies and different things that were being tried, but more or less, this is sort of the general idea of what was being done. And the advantage of this is that it's robust, it's computationally fast, it's a single inverse Fourier transform. But the disadvantage is, I think we're all aware of, is that this leads to low quality reconstructions. So here's a typical example from X-ray CT, and this is the type of artifacts you get. So this is the classical artifacts from filtered back projection with subsample measurements. So what happened in sort of the 2000s was that compressed sensing came along. And so, especially in the context of imaging, this was really initiated by this famous paper by Candace, Romberg, and Tal. And what was perhaps, certainly for practitioners, what was perhaps most influential was this experiment that was performed therein. So what they did was they took the Shep-Lonergan phantom image, they took Fourier samples of this, so they did radial sampling in Fourier space. So here's the classical reconstruction, the zero-padded Fourier transform, showing significant artifacts. But what they showed is by changing the reconstruction to a compressed sensing approach based on TV minimization, they could recover this image exactly down to numerical error. So this spurred a significant amount of interest in compressed sensing and compressed sensing for image reconstruction. And very quickly, people started to use this and apply this in applications. So for instance, probably MRI was the first due to the work of Mickey Lustig and collaborators. And since then, compressed sensing has been used in a lot of different applications, or tried for a lot of different applications. And it's now something that's had actual impact in commercial devices. So in 2017, compressed sensing techniques received FDA approval. And now you can actually buy scanners that use these techniques. So his Philips and Siemens and GE, they all now have a compressed sensing implementation in their scanners. So this is not a talk about compressed sensing per se, or it's not a talk about compressed sensing really, but I wanted to sort of just highlight that the compressed sensing was sort of, in some sense, the first revolution in compressive imaging. And it really sort of changed the way, in some sense, that we think about how to perform image reconstruction. So rather than simple linear reconstruction strategies, we now think about nonlinear reconstruction algorithms that exploit some kind of low dimensional structure in the images that we're trying to recover. Oh, there we go. So let me say a couple of more things about compressed sensing. I don't want to go into too much details, but it's useful to introduce a few terms that might crop up in various places later. So in half a slide, how does compressed sensing work? It's basically requires three stages. So we first of all choose a model. So we assume some kind of sparsity or some kind of structured sparsity in a sparsifying transform. So for example, wavelets or discrete gradient or something like that. And then we design a reconstruction procedure or a decoder to exploit this structure. So a typical example, so we know that if we have sparsity in, say, wavelets or TV, then this can be exploited effectively by minimizing an L1 norm. So a typical decoder you might write down is something like the lasso here, where you minimize a weighted sum of this L1 norm penalty, which promotes sparsity, and a data fidelity term here. Okay, so that's the first two stages. And then the final stage is obviously you need an algorithm to solve this optimization problem. And nowadays, because of the sort of the developments in compressed sensing, there's sort of an abundance of fast algorithms for solving these types of problems. So whether they be proximal gradient type methods, say, for instance, FISTA, or splitting methods such as ADMM or the Chambord-Pock algorithm, things like that. Nowadays, we have a lot of good algorithms and also software for solving these types of problems at large scale. So I guess the point I'm really making here is that sort of compressed sensing was sort of, in some sense, the first revolution in compressive imaging, and it's now reached a fairly mature state. The use of compressed sensing for image reconstructions is now something that we understand how to do pretty well. I'm not going to go into any of these details, but you know, when I say that this is mature, we understand things like how to effectively sample in compressed sensing to exploit sparsity. We know that there are recovery guarantees that assert stability and accuracy of the recovery through the compressed sensing theory, so properties such as the RIP, the robust null space property, things like that. And we also know how to do sort of many sort of generalizations and variations on this theme here. So this is in some sense the bread and butter compressed sensing approach using wavelets or TV and solving something like lasso. There are many ways in which you can sort of boost the performance of this. So you can go to more fancy sparsifying transforms like curvelets or shearlets, or higher order TV like TGV and things like that. And you can change this procedure. Maybe you use some kind of weighted or re-weighted strategy or some non-convex penalty, et cetera, et cetera. And then finally, as I mentioned, now there's a lot of fast algorithms to solve this problem efficiently. Okay, so that's a sort of short introduction to compressive imaging, sort of what's come before. Now I want to talk about deep learning for imaging. So, okay, so first of all, deep learning. So I think most people in the audience will be sort of aware that, you know, obviously there's this deep learning. There's this huge wave of deep learning that's taken over in the last 7 or 8 years. And this sort of began, the modern sort of deep learning renaissance began in around 2012, where famously deep learning won this, this ImageNet large-scale visual recognition challenge. So this is an open competition using the ImageNet database for image classification. Pre-2012, the sort of winners were based on things like support vector machines. And post-2012, all the subsequent winners have been based on deep learning using convolutional neural nets. So this sort of started a sort of wave of activity in deep learning, and in particular in imaging. Deep learning is now sort of proving to give state-of-the-art performance on a variety of different imaging tasks. So ranging from classification and segmentation to image restoration tasks such as denoising, deblurring, super resolution, and also inpainting. And in some cases, such as denoising, this is sort of becoming a standard of how you can do these tasks. So, for instance, in MATLAB, very recently, I became aware that now MATLAB's denoise image command actually has an option to use a convolutional neural net. So here's an example here of denoising using that. So given this sort of wave of interest in using deep learning for imaging tasks, it's not surprising in any sense that people have begun to look at using deep learning to solve image reconstruction problems. But I want to talk for a couple of minutes about sort of why one might do this. And the sort of arguments or the common arguments that have been given for using deep learning for image reconstruction instead of something like compressed sensing often stem from some of the limitations of compressed sensing. So let me talk about a couple of these for a few minutes. So one of the limitations of compressed sensing is that it's often described as a model-based approach. In that, what is meant by that is that one is imposing a fixed image model, so sparsity in wavelets or sparsity in gradient or something like that. On the other hand, we know we have this sense from classification that neural networks can sort of implicitly encode complex image structures. So there's this sense that, well, rather than choosing a fixed model, which might not be optimal for a particular imaging modality, why not train neural networks to find some more refined image structure, or to implicitly find some more complex image structure. The second argument is that compressed sensing procedures are generally, in inverted commas, handcrafted. And what's meant by that is that once you have a model, such as sparsity in wavelets or sparsity in gradient, then you have to design a functional that exploits this structure. So for instance, L1 minimization or TV minimization. And this is where things can get difficult. So it's easy. It's not difficult to come up with more sophisticated models for images. in this stage here. But then it's difficult to design a reconstruction procedure that can exploit more complex structures. Now, of course, you can write down a very complicated reconstruction procedure, but at the end of the day, this needs to be something that you can actually compute solutions of. So if you write down a very complicated functional, it might not be trivial to devise an algorithm that can solve the optimization problem. So here the idea is, okay, maybe we can instead, rather than handcrafting something, we can train a neural network to perform the reconstruction. A sort of third sort of argument that's given is that any kind of optimization-based recovery procedure is relatively slow. To solve something like the lasso, we typically need to perform sort of hundreds of matrix vector multiplication. So you're talking on the order of hundreds or maybe thousands Fourier transforms, for instance. On the other hand, while training a neural network is very slow, if you've trained a neural network that's not too deep, then and not too wide, then propagating forwards through the network, which is what you would then need to perform the reconstruction, is relatively fast. And then the final argument is that one of the things that's quite crucial to get good results from compressed sensing-based procedures is that the parameters in the optimization algorithm you use are well-tuned. And this can be a fairly delicate process, and one that can have quite a big effect on the image quality. So the sense here is, okay, maybe we can, rather than tuning these by hand in some way, maybe these can be learned instead. So that can be thrown into the set of learnable neural network parameters. Okay.
So Ben, there's a question about essentially, once we choose a neural network topology, isn't it like assuming a fixed model?
In a sense, but it's a more complex model. So something like a sparsity model is a sort of fairly simple union of subspace model, right? When we pick a neural network architecture, that's a much more complex model in some sense. So I would say that also that we're not explicitly we're not sort of making an explicit choice of the model. It's sort of somehow implicitly encoded in the neural network, right? So, and then so the other thing to say as well is, okay, so we're also learning the parameters of the model from training data, right? Whereas when you choose something like sparsity, right, that's independent of any training data you have. Right?
Okay, thanks.
Okay, so this is why one might use deep learning for image reconstruction. Let me talk a little bit about sort of different ways in which one might do this. So I don't want to get too deep into the weeds here because there are a lot of different approaches out there. There are a lot of different technical details, but let me just try and give a sort of flavor of the different methodologies that people have tried. So let's assume theta is our training data. So here our training data consists of pairs, which are pairs of measurements yi and images xi. Okay. So the most simple approach is to simply just learn a neural network that is a mapping directly from the measurement space to the image space. So this is sort of conceptually the simplest thing to do. And it has another advantage in that it's not limited by the accuracy of your forwards model. So in other words, here you're not using any information about your measurement matrix A. And that can be beneficial because in some applications, or in all applications, your matrix A represents an idealization of the underlying physics of the acquisition. So if you commit modeling errors in deriving A, then that can lead to artifacts in the recovered images. due to model mismatch, essentially. So here, because you're learning and mapping directly from the measurements to the images, you're not limited by that forwards model. The disadvantage is that generally to get something like this to work, you need at least several fully connected layers, because it's not, you can't reasonably assume in applications typically that your forwards model is going to be represented by just convolutional layers. So because you need sort of fully connected layers to do this, the number of parameters you have to learn very rapidly gets very, very large, which means that doing this kind of approach for higher resolution problems is very challenging. Just computationally, there are too many parameters to learn. So a different approach is sort of what's called the denoiser network approach. And so here, the idea is to take the measurements and then first perform a cheap reconstruction on them. So this could be a classical linear reconstruction, such as a zero-padded Fourier transform or filtered back projection. And then the idea is to train a network that denoises from the artifacts that you get from this cheap reconstruction. So we know that neural networks are good at denoising for things like Gaussian noise. So there's sort of potential to use neural networks as well to denoise the specific type of artifacts that you get from this kind of linear reconstruction. So this is good. You can do this with convolutional neural networks, so it's more efficient. You can scale it to larger scale problems, but it does have the limitation that you're using the forwards model. So anything that you lose in performing this reconstruction that was in your original measurements, it's difficult to get that back. Okay, so then the sort of third methodology is unraveling. So in a sense, this is not really distinct from the first two things I talked about, but it is a slightly different approach. So one of the things I didn't sort of mention anything about when we're talking here is how do you choose the neural network architecture? And the idea of unraveling is to give you a sort of principled way of designing network architectures. And the basis for this is something like the following. So if we do some kind of compressed sensing approach, then we end up minimizing something that looks like this. So f of z here is the functional that's promoting your sparsity or whatever structure that you want to promote. And a standard way to solve the lasso would be to use something like a proximal gradient algorithm, in which case the iterations look something like this. And if one stares at this for a couple of seconds, it's clear that this looks like a layer of a neural network. So this is an affine map of Zn, and then the proximal map is a nonlinear function. And often, if you have if your f of z is a separable function, then proximal map will act component-wise. So it now starts to look pretty similar to a standard sort of activation function in a neural network. So the idea of unraveling is to take a standard optimization algorithm for solving the lasso, for instance. So this could be the proximal gradient method or ADMM or primal dual iteration or something like that, and to reinterpret that as a neural network. So after n steps, we get an n-layer neural network, basically. Now the idea is to say, okay, let's learn some component of that neural network instead. So we could learn the weights and biases here, or you could actually learn the proximal map instead. So there are different ways you can do this. And you might also learn the optimization parameters as well. So the advantage of this is, again, it's a principled way to design architectures. The obvious disadvantage is it's tied to the optimization solver that you use. So that might have some limitations. So as I mentioned at the start of the talk, in the last few years, deep learning, the use of deep learning in image reconstruction has been subject to a lot of interest. And there are a lot of papers and a lot of different strategies that have been proposed over the last few years. And many of these claim that deep learning is offering sort of state-of-the-art performance for image reconstruction. So maybe I'll single out this Nature Methods research highlight article here, where the title is AI Transformed Image Reconstruction. And it mentions that a deep learning-based approach improves the speed, accuracy, and robustness of biomedical image reconstruction. So then the question I want to spend the rest of the talk on, or the question to motivate the rest of the talk, is should we be concerned? Or is there any sort of anything that's going to cause pause or caution when designing deep learning approaches for image reconstruction? And for the rest of the talk, I'm going to talk about the issues surrounding instabilities of these approaches. So let me move on to instabilities in deep learning. So the story about instabilities does not start with image reconstruction. This actually comes from the classification problem. So in 2014, there was this paper that was published entitled "Intriguing Properties of Neural Networks." And what they did in this paper is they took trained neural networks for solving image classification problems. So by that I mean you have a network. The input is an image, and the output is a label. So it could be the label is a cat or a dog or a horse or whatever. And what they showed is that they were able to, given an image, they were able to construct a small perturbation of this image, such that when they fed that perturbed image into the network, it would produce completely the wrong label. So this image, say the original image was a cat, and they would make a small perturbation to it. It would still look like a cat to the human eye, but suddenly the label would now be a dog. So here are examples of sort of what I mean here. This is from a later paper called Universal Adversarial Perturbations. So you might not be able to see on your screens here, but I can sort of just make out the little perturbations that are in these images here. You might see them as sort of textures. And you can see all these images have been misclassified, even though clearly this is a whale, and clearly this is a dog, and clearly this is a sock. And so this, as I mentioned, this was first observed in 2014, and since then in the sort of machine learning community, there's developed a sort of fairly active area of research that looks at this phenomenon of what are called adversarial perturbations. So generally speaking, the people sort of look at, well, different algorithms for constructing these perturbations. So I should point out, emphasize here that the perturbation is not random. It's designed to cause the wrong output on the network. So it's sometimes referred to as an adversarial attack, in the sense of you can think of some kind of malicious actor who wants to cause your network to misclassify. More about that in a moment. So the sort of research that's sort of focused on different algorithms for constructing these, understanding sort of the network properties that give rise to these instabilities, and then finally sort of how you defend against these attacks. So in some sense, you can sort of view this as kind of an arms race in some sense, where one side of this community is constructing algorithms to construct attacks, and then another side of the community is trying to defend against them. And suddenly, so you come up with a defense, and then I try and break it, and et cetera, et cetera. So I think what's important to point out while we're sort of doing this detour into the classification problem is that these are not just theoretical curiosities. These play into this sort of general sense that decision-making using deep learning algorithms is mysterious. That the ways in which a neural network makes decisions or makes classification decisions, for instance, is it's not clear what features are being learned to make those decisions. Okay? So if you can make a small perturbation that doesn't change the image as far as the human eye is concerned, but it changes the classification, this says that the features are being learned are perhaps not the ones that we would recognize as the important features. More concretely, people have actually started constructing these adversarial attacks in actual applications. So I think people in the audience might have seen these kind of adversarial patches that you can wear. There are also adversarial eyeglasses that can fool surveillance systems. And people have also constructed patches that you can put on stop signs that can fool self-driving cars, essentially. Finally, there's also been some work on medical insurance or medical insurance fraud, and how you can use adversarial attacks to potentially commit medical insurance fraud. So this is the idea that medical insurance claims are increasingly automated, and so if you're a malicious actor, you can design these kind of attacks to change the outcome of a claim.
So there's a question from the audience from François Vignon asking if you need to have access to the network to design the adversarial perturbations, or how it's done in these examples.
That's an excellent question. So there are, so if you dig into the literature on this, and I'm happy to provide some references afterwards, there are different types of attacks. So there are attacks where you need access to the network architecture. And I think these are known as white box attacks in the community, but then there are also strategies for black box attacks where you don't need access to the network architecture. One of the other things as well is what's was shown in this paper here is that these perturbations that you create can also be transferable. So suppose I have access to a network and I create adversarial attacks for that network. I can actually, in some cases, take those adversarial attacks and apply them to a different network, and it will still cause misclassification. So, yeah, so you don't necessarily need access to the network architecture to do this. Okay, okay, so this is sort of a classification problem. Now let's get back to image reconstruction. So a couple of years ago, we thought about this and thought, okay, well, could a similar phenomenon occur in image reconstruction? So if you have a trained neural network for reconstructing images, could it be the case that if you make a small perturbation to the input, which in this case are your measurements, can that cause a large effect on the output? So we wrote a paper on this, which just appeared in PNAS. And in this paper, we demonstrated these perturbations for different network architectures. So what we did is we took half a dozen networks for image reconstruction that were out there at the time. And for each one, we showed that you can construct these perturbations. So let me show a few results from this paper. So here's one of the networks. This is for an MRI problem. Here's the original image. And here's the reconstruction that this network gives from the measurements of this image. Okay, so these are of the form AX. And so you can see here that this image is recovered very well. Okay, there's no noticeable artifacts in the recovery here. This is a very high performing network for these types of images. So what we're going to do now is we're going to try and find a perturbation of the image that causes a large effect here. So the way in which we do this is we try and optimize the following functional. So here we have a term that is promoting dissimilarity between the recovered images. And then we have another term here that's trying to keep the perturbations small, okay? Because obviously We're interested in small perturbations that have a large effect. So this is a non-convex optimization problem. We solve it just by running gradient descent. We don't make any claims that we find a maximum, but it doesn't matter because we're just interested in constructing a perturbation. So we just run a fixed number of steps of gradient descent. So getting back to the question that was previously asked, in order to do this, we need access to the network. And to run gradient descent on this, we need to use backpropagation to find the various gradients. Okay, so here's an example. So this is the first perturbation, and you can see that it has no effect on the image here, but it's had a significant effect on the reconstruction here. Then what we can do is we can run a few more steps of gradient descent and find perturbations that are larger in norm. So here's R2. Maybe you can start to see a few artifacts in here. But now this has had a very significant effect on this image. You see these stripy artifacts. We can do a little bit more. And now again, you can see there's a substantial effect on the image. And so the point here is that if you look at this image, if you got this image out of an MRI, you could immediately look at this and say something has gone wrong here with the acquisition. Okay, there's some corruption in the data that's caused the image. We just need to redo the scan. But if I go to this example, it's really not clear that something has gone obviously wrong here. These features that you have here are things that you may not recognize as clearly non-physical artifacts. So we can sort of range, the phenomenon can range from things that are sort of seemingly physical to things that are clearly unphysical, and therefore hard to, difficult to defend against in a sense. Let me just, for comparison, show you a compressed sensing reconstruction on the same perturbed image. So with compressed sensing, again, because we know that compressed sensing is stable to perturbations, we don't see these significant effects. Okay, let me show another example. This is this automap network. This is an example of this fully trained model approach. So it's the same kind of experiment. We start adding these perturbations and you can see immediately you get very substantial effects on your image. Again, on the other hand, compressed sensing doesn't see these substantial effects because it's inherently stable. There's another experiment here on a couple of other networks, which I think I'll skip. But let me sort of talk about some rare events. So what we did in these previous examples, so going back to here, is we are finding a perturbation that's designed to cause the maximum effect. Okay. So the obvious question that comes up is, well, is this a rare event? Is there just is the set of perturbations that cause bad artifacts a set of measure zero? And it turns out that this is not generally the case. In fact, in certain scenarios, purely random perturbations can produce bad effects. So here's the same example. And what we did here is we did 100 random perturbations and then looked through the reconstructions and visually found the one that looked the worst in the eyeball metric. And you can see this artifact occurring here. That's not present in the true image and is also not present in the compressed sensing reconstruction. So this is the worst out of 100. If you take the worst out of 20, you can still see an artifact. It's not quite as significant, but it's still there. So, okay, so we know these instabilities occur. What I want to talk about next is sort of why they occur. And it turns out that there's actually a fairly straightforward explanation, or there's a fairly straightforward mechanism that can cause these instabilities. And this is what we call the lack of kernel awareness. And by this, I mean the following. When you do training, it's very hard, or it's it's very hard to avoid the following scenario. So suppose I have two images, X and X primed, and these, think of these as being distinct, as being far apart. But when I project them into the measurement space, they give measurements that are nearly the same. So Y and Y primed are close together. Now, Y and Y primed are what I'm going to see when I want to perform the reconstruction. So it shouldn't be possible to recover X and X primed accurately from the measurements I see, because the measurements are close to each other. But I can always set up a training procedure where I can do this. Okay, so I can, think about X and X primed as being in my training set. If I'm able to drive my my training error down to 0, then I can always find a network that's going to recover X prime very well and recover X very well, even though Y and Y primed are very close to each other. But it should perhaps not come as a surprise that this is going to cause instabilities. And here's the theorem that explains it. So suppose, so this is a theorem that we proved that's in this, this paper here, which is on the archive. And what this theorem says is the following. So suppose you have a continuous mapping, and this is your reconstruction map. So it's going to take your measurements and give you your reconstructed image. And suppose there's some eta greater than 0. And suppose your mapping is such that you recover X to within accuracy of eta, and you recover X prime to within an accuracy of eta, but X minus X prime lies close to the kernel or the null space of your forwards operator. Okay, so this is measured by eta. Then necessarily you have a large Lipschitz constant. So there's a closed ball centered at the measurements y equals ax, such that the Lipschitz constant for any point in this ball is bounded below by the norm of x minus x primed minus 2 eta divided by epsilon. And this is for any epsilon greater than or equal to eta. So the way in which to think about this is think about what happens as I drive eta to 0. So as I train better and better, so I recover x and x prime better and better with my neural network, then my Lipschitz constant is blowing up like 1 over epsilon. So that's showing me that I'm going to become unstable. There are also two other consequences of this theorem as well, which are that under the same conditions, you can also get both false positives and false negatives. And I'm going to not worry about the technical statements here, and I think I'm just going to actually show an experiment of these. So this is also in the paper. So here's the experiment. So here are the two images. So this is X, and this is X primed. And you can think about X as, think about this as a sort of one-dimensional brain. And this is a healthy brain. And this is an unhealthy brain that has a tumor in it. So X prime is different from X because it has this little tumor here. Okay, this thing Z. And so what we've done is we've trained a neural network here to recover X and recover X prime very well from their measurements. But this feature lies close to the null space of the measurement operator. So we're taking Fourier measurements, and we're taking primarily low frequency Fourier measurements. This is typical in practice, and this thing is therefore, because its Fourier transform is small at low frequencies, it's therefore close to the null space. And so now what can happen is you can find a perturbation of your measurements that causes you to not reconstruct X, but now you reconstruct X primed here. So this is a false positive because you should be reconstructing X, but you're actually getting X primed. Similarly, for X primed, you can find another perturbation of your measurements that's now going to give you X. So you have this false negative now. So, okay, so what we've seen up to this point is, okay, these instabilities occur, and we can sort of understand why they occur in terms of this kernel awareness. So what I want to spend the rest of the talk doing is talking about, well, what can we do about this? How should we sort of proceed with this in mind? So the first thing to obviously when one becomes aware of instabilities or becomes aware that an algorithm is unstable, the first thing to think is to say, okay, well, is there a sort of easy way to modify the algorithm to make it more stable? And the point I want to make is that this is not something that's easy to fix. And I'm going to make this point by just going through sort of 4 different strategies that that have been tried or have been proposed as ways that might give you better stability. So the first such strategy is to add random noise to the measurements. This seems like, in some sense, a reasonable thing. There's a hope that if you have some bad perturbation in your measurements, that maybe you can sort of wash it out with some random noise. And in fact, this is something that has been done in image classification to try and defend against adversarial attacks. And this would work if the perturbations were rare events, but they're not. And in fact, we saw an example of purely random perturbations where you could still have bad artifacts. And moreover, because in the theorem states that these bad perturbations occur in pools, this means that adding random noise to a bad perturbation is not going to cure it, or not necessarily going to cure it. A second approach, so something else that's also used in image classification, in fact, this is perhaps the state-of-the-art defense strategy in image classification, is to perform some kind of adversarial training. So here you try and set up, in your training, you set up this adversarial game where one person tries to train the network that accurately recovers the images in the training set, and then the other person tries to construct bad perturbations of those images in the training set to badly affect the network that was trained by the first player. And then you iterate between these two things, and you hope at the end of the day you get something that's more robust to perturbations. So this is actually something that some of the networks that I mentioned previously actually do. And the tricky part here is that it turns out that setting the regularization parameter in this is actually a highly unstable problem in itself, one that depends on your matrix A and your training set. So this can be very delicate to try and set this up to get better stability. It turns out that finding the lambda to make this work effectively can be challenging. Okay, so two other approaches. So one other approach is to try and enforce consistency in the reconstruction. So this is something that's been used a little bit. This is the idea that you try and make sure that your reconstruction, when you pass it through your forwards operator, it returns you the same measurements. But you can actually see from this theorem that this actually is not going to do anything to affect this scenario here. Consistency doesn't really have anything to do with these conditions that came up in this theorem. Another approach is to train with multiple sampling patterns. So if you take something like MRI or CT, or let's say MRI, this means maybe using different numbers of radial lines, things like that, or maybe some radial lines, some spiral sampling patterns. Maybe just have a bunch of these and train using that. So this in some sense could be viewed as a sort of data augmentation strategy, because you're creating a bigger training set. But the point is when you actually come to use this, when you come to use the network that you've trained here, you're using it on a fixed sampling pattern. You don't have access to the measurements from all the different sampling patterns. So actually, in some sense, this might make it easier to attain these conditions, or easier to attain the first two conditions here, because you might be able to do better training. whereas you won't affect this because when you use it, you're using only a fixed A. Okay, so so given that there's sort of no easy sort of ways seemingly to sort of stabilize things, it's worth sort of approaching this problem from a slightly different perspective and say, okay, well, let's try and understand how to get more stable mappings. So obviously, it's very easy to come up with a completely stable mapping. The zero map is a perfectly stable reconstruction map. But of course, we want to guarantee performance. We want a high accuracy in our recovered images. And as one can imagine, there's a trade-off between performance and stability. And so to see this, we did a sort of further series of experiments to try and understand this kind of trade-off in the network. So let me just show a few of these experiments. So this is this L50 network. Here's a typical image that's close to the training set. And what we've done is we've added a small detail to this image. So here you can see this. This is, of course, not something that's seen in the training set, but you can imagine maybe this is a feature that might come up in some later use of this network. And now we try and reconstruct this image. So this network completely washes out this detail, whereas compressed sensing recovers it quite nicely. And so in this sense, it doesn't, its performance is not great. But the flip side of this is actually a fairly stable network. So it has good stability, but not great accuracy. And you can see this trend as you look at different networks and perform the same experiments. This is a network that's somewhere this is sort of moderately unstable and moderately accurate. You can see it sort of washes out this detail a little bit, but you get a little bit more of it than in the previous network. Then if we go back to this network that I showed previously, this is very accurate. So it recovers this detail very well, certainly the best out of all the networks. But it's highly unstable. So
just a quick question. You're using the same number and type of measurements, I'm assuming, in all of these, only the reconstruction?
No. So it's a different setup for each network because, and I'm actually just about to talk about this. So each network is trained with a particular setup, which means say Fourier measurements or radon measurements, and with a particular sampling strategy. So
okay, but this person on this particular slide, for example, the compressive sensing algorithm you're using is using the same measurements as you.
It uses exactly the same measurements. Yes,
from slide to slide. Okay.
Yeah.
Thanks.
So actually that leads me sort of quite nicely onto the next point. So as I was just saying, so each of these networks is trained on a specific sampling percentage. So you can actually see them here. So this network is trained at a 20% sampling percentage. So one of the other things that we did was to actually change the sampling percentage. So either increase the number of measurements that you feed into the network or decrease the number of measurements, and see how that affects the reconstruction accuracy. And one of the interesting things here is that this can actually be quite strange, is that actually the accuracy can decrease as you increase the number of measurements. So this happens for this network and these networks here. And then the other two networks, it increases as one might expect. So this is a sort of interesting phenomenon. It's obviously quite bizarre that you would think if you feed more measurements into a reconstruction procedure, it should certainly do no worse. And you would hope it does better. The sort of practical implication of this is that if you want to design neural networks for something like MRI, then you might actually have to have a different one for each different sampling pattern in the machine. So that's a practical implication. a theoretical implication of this is that this kind of phenomenon suggests that somehow guaranteeing the performance of a network is quite subtle. If it's highly dependent on the sampling rate that you train at, then it's not clear how the network is going to perform in practice. Okay, so I'm running behind, so I'm going to skip this slide. So we have some insights into this as well, which are in the paper, but I'm gonna skip through those, and I want to sort of rapidly move towards the sort of final point. So just to sort of sum up where we are at this point, so we've shown that sort of existing deep learning approaches are often unstable. It's not easy to overcome these instabilities, and there's this stability performance trade-off. As you perform better and better, you generally get less stable. And finally, this performance, it's hard to predict the kind of performance that you get. And the slide that I skipped can be summarized as also saying that we know that there are settings where training is not enough, standard training is not enough to give you good performance. So this raises the question, well, can we compute accurate and stable neural networks? And to get some insight here, obviously we need to think about this mathematically. We need to formalize a class of problems that we wish to solve. And so rather than sort of starting from a sort of very high point, the sort of point I want to start with is to say, okay, let's be slightly more cautious, and let's show that we can at least perform as well as compressed sensing. So the point is we know the performance and accuracy of compressed sensing. Let's show that we can at least do as well as that with neural networks. So what this means mathematically is we're going to take a class of matrices, script A, and these are going to be matrices that have this robust null space property of order S with certain constants. These constants don't really matter. And now for each matrix, we're going to think about the family of measurement vectors. And these are the measurement vectors that we get from images or vectors X that are approximately S sparse, okay, and where the noise is not too large. Okay? So think about this as given A, this is the class of vectors X that we can recover accurately with compressed sensing. In particular, the error is bounded by this zeta here. Okay, so I should say here you can consider a lot more advanced setups than this. You can consider things more relevant to imaging, like structured sparsity models. But just to keep it simple, this is what I'll talk about. So the idea is we know that for this problem with compressed sensing, we can achieve an order zeta error here. And we know that there exists a neural network that can achieve the same error. So we can appeal to all this this approximation theory literature on the existence of neural networks with certain properties to show that there exists a neural network that does this. But of course, we're interested in computations. We're interested in an algorithm that can compute a neural network to solve a certain problem. So to conclude, here's the theorem. And so this theorem says the following. The theorem says there exists an algorithm which, given a matrix in this class, can compute a neural network that achieves this order zeta accuracy over this class of inputs. And we have some guarantees on the size of the network, so the number of layers and the widths as well. So I should say I can't take too much credit for this result myself. The credit, much of the credit should be given to Matt Colebrook, and he's writing a paper that's nearly finished that will have some of these results plus many more. What I should say is that this is not just a completely theoretical thing. You can actually implement this network. We've done it, and it is stable, and it does sort of deliver the accuracy that we would expect it to. So here's this experiment where we now actually construct adversarial perturbations for this network in the same way. So these are the adversarial perturbations, and then we run them through the network, and you can see that it's not affected by these instabilities because it's a stable neural network through the way in which we constructed it. Okay, so I've run a little bit over, which I apologize for. So let me sort of finish with that. And thank you for your attention, and point you towards the papers on which this work was based. Okay, so thank you.
All right, thanks a lot. Excellent talk. We appreciate you coming to the seminar, virtually, of course, to tell us about deep learning. For anyone who has questions, feel free to put a question to the Q&A tool here, and I think I have a few questions for you, Ben. So maybe I'll just answer one here. So on slide 35, if you want to go back, an audience member wants to know if the architectures are fixed as the subsampling rates change.
Yes, sorry. So what we do here is, so these are all trained neural network architectures. And so what we do is so we're not retraining the network here. We're just feeding in a different number of measurements. So the way in which you do this, so if you, most of these networks are sort of denoiser type networks. So they first do some kind of linear reconstruction, and then it's propagated through a network. So it's very easy to change the number of measurements there. You just, if the linear reconstruction is like an inverse FFT or a zero padded FFT, you're just doing a different zero padding. So.
Okay. Any other organizers should jump in anytime they want to answer other questions. Let me just